Dear students, welcome to the next lecture on aromatic hydrocarbons. In this lecture, we shall discuss about the characteristics of the aromatic molecule benzene. Benzene or C6H6 is a planar molecule containing a ring of 6 carbon atoms, and each carbon is attached to one hydrogen atom. The 6 carbons of benzene form a perfectly regular hexagon, and all the carbon-carbon bonds are of same bond length, which is in between the bond length of CC single bond and CC double bond. There are delocalized electrons which gives extra stability to the benzene ring. Due to the delocalization of electrons, benzene resists addition reactions. The molecule only undergoes electrophilic substitution reactions like halogenation, nitration, sulfonation, etc. As it does not respond to addition reactions, benzene does not decolorize KMnO4. Usually, unsaturated molecules decolorize KMnO4 and form corresponding diols. And benzene does not undergo this reaction. The delocalization energy and the stability of benzene can also be explained on the basis of heat of hydrogenation. The heat of hydrogenation is the enthalpy change when H2 molecule is added across an unsaturated bond. The heat of hydrogenation value of cyclohexene is minus 119.6 kilojoules per mole, and that of 1,3-cyclohexadiene is almost double this value, that is minus 231 kilojoules per mole. In cyclohexadiene, two molecules of H2 will add across the two double bonds. So if we consider benzene as a molecule with 3 double bonds, we would expect a theoretical value of minus 358.8 kilojoules per mole. But the actual heat of hydrogenation value of benzene that is found experimentally is minus 208.3 kilojoules per mole. The difference between this actual value, this experimental value, and the theoretical value is 150.5 kilojoules per mole. And this can be considered as the resonance energy or the delocalization energy of benzene. This high value of delocalization energy indicates that the delocalized electrons provide much stability to the benzene ring. Kekulé structure of benzene. Kekulé suggested that the 6 carbon atoms of benzene molecule form a hexagonal ring with alternate double and single bonds. According to him, these double and single bonds change their positions to give equivalent structure, and there exists a dynamic equilibrium between the two equivalent structures of benzene. And this structural illustration by Kekulé had several limitations because it could not explain the stability of benzene towards strong oxidizing agents like KMnO4. And further, it was found that the carbon-carbon bond length of benzene is 1.39 Armstrong, which is in between the value of a CC double bond and CC single bond. And the next concept was the resonance concept, in which benzene exists in several resonance forms. The resonance forms of benzene are shown in the figure. Structure 1 and 2 represent the Kekuli structures, which are the mainly contributing structures. Structures 3, 4 and 5 are called Diva structures or feebly contributing structures of benzene. And the resonance hybrid of benzene can be represented as a hexagonal ring with a circle inside, and the circle denotes the delocalized electrons. Next is the molecular orbital theory description of benzene. According to molecular orbital theory, all the carbon atoms in benzene are sp2 hybridized. The two sp2 hybridized orbital of each carbon atom overlap with sp2 hybrid orbitals of two neighboring carbon atoms and form CC sigma bonds. Thus, there are 6 sigma bonds formed between the 6 carbon atoms, which are held at 120 degree apart. So each carbon atom has 3 sp2 hybridized orbital, out of which 2 are used for carbon-carbon single bonds. And the remaining sp2 hybridized orbital of each carbon atom. So there are total 6 sp2 hybridized orbitals remaining, will overlap with the 1s orbital of 1 hydrogen each, and thus forms CH sigma bonds. In total, there are 6 CH sigma bonds. And the molecule will have a planar structure with a hexagonal ring of carbon atoms. The structure is shown in the figure. The sp2 hybridized orbitals are held at 120 degree in the same plane, and it overlaps with the neighboring carbon atoms, and one sp2 hybridized orbital of each carbon overlaps with the 1s orbital of hydrogen, forming CH sigma bonds. Each carbon atom in the benzene ring has an unhybridized 2pz orbital lying perpendicular to the plane of the carbon-carbon hexagonal ring. And this unhybridized orbital contains 1 electron each. These orbitals produce pi molecular orbitals containing 6 electrons. The half of the unhybridized pz orbital lie above the plane and the other half lie below the plane. These 6 p orbitals can overlap in 2 different fashions. That is, if we number the carbon atoms, the carbon 1 can either overlap with carbon 2 the pz orbital of carbon 1 can overlap with carbon 2, or the carbon 1 can overlap with carbon 6. So there are two possibilities. 1 overlaps with 2, 3 overlaps with 4, 5 overlaps with 6, or 1 and 6, 2 and 3, 4 and 5 combination. And the overlap of these two pz orbitals result in the formation of a delocalized pi bond which can extend all over the ring. And as a result of this delocalization, benzene is highly stable, and the extra stabilization energy is called the delocalization energy, which is minus 150.5 kilojoules per mole. All the carbon atoms of the benzene ring have the same bond length, 1.39 angstrom or 139 picometer. Thus, according to the molecular orbital theory, the unhybridized p orbitals overlaps with each other and form a delocalized electron cloud, pi electron cloud, as shown in the figure. The bond angle is 120 degree. The CC bond length is 139 picometer. CH bond length is 110 picometer in benzene. According to molecular orbital theory, the 6 overlapping p orbitals combine together to form a set of 6 pi molecular orbitals. The 2 pz orbitals of 6 carbons, the atomic orbitals, combine together to form 6 molecular orbitals. Out of these 6 molecular orbitals, 3 are of lower energy and 3 are of higher energy. The lower energy molecular orbitals are called bonding molecular orbitals, and the higher energy orbitals are called anti-bonding molecular orbitals. Each molecular orbital accommodates 2 electrons with opposite spins. So in the ground state of benzene, the 6 electrons will occupy the 3 bonding molecular orbitals, and no electrons are found in the anti-bonding orbitals. Thus, the benzene molecule is said to have a close bonding shell of delocalized pi electrons. And this close bonding shell partly accounts for the stability of the molecule. The pi molecular orbitals of benzene are shown in the figure.